So, today we will discuss inverse response compensator. Inverse response compensator. In the last class we discussed the date time compensator. Inverse response compensator can be derived based on the same concept. Now, inverse response behavior we studied earlier, fine. Inverse response behavior we studied earlier. Inverse response behavior is the net result of two opposing effects. Inverse response behavior is the net result of two opposing effects. Fine. What is the condition for inverse response behavior? What is the condition for inverse response? Transfer function has a positive 0. Transfer function should have positive 0, then only the inverse response behavior is obtained. Now, this inverse response compensator was proposed by Inoue and Alt Peter in 1962 based on the general concept of Smith predictor or date time compensator. They have proposed this inverse response compensator based on the general concept of Smith predictor or date time compensator. Fine. Next, we will discuss the development of inverse response compensator. Next, we will discuss the development of inverse response compensator. Consider two first order processes acting in parallel. Consider two first order processes acting in parallel, and the first order processes are represented by k p 1 divided by tau p 1 s plus 1 and another process has the transfer function of k p 2 divided by tau p 2 s plus 1. These two first order processes acting in parallel. Input to these first order processes is f. This is the input. Now, it is mentioned that inverse response behavior is the net result of two opposing effects. So, we will consider one output positive, another output negative. Fine. Then the output is say y. Fine. It is obvious that these two first order processes are acting in parallel and they have opposing effects. Now, we can write the expression for y as k p 1 divided by tau p 1 s plus 1 minus k p 2 divided by tau p 2 s plus 1 multiplied by f bar. Can we write this? Output equal to transfer function multiplied by input. Rearranging this, we can write as k p 1 tau p 2 minus k p 2 tau p 1 s plus k p 1 minus k p 2 divided by tau p 1 s plus 1 multiplied by tau p 2 s plus 1 f. Fine. This we can get from this expression. Now, can we find the 0 from this expression? What will be the expression for 0? Minus k p 1 minus k p 2 divided by k p 1 tau p 2 minus k p 2 tau p 1. This is the 0. Agree? So, what is the condition for inverse response behavior? This 0 should be positive. That means, the condition is this should be greater than 0. This is the condition for inverse response behavior. Fine. Next, we will implement the controller. I mean, we want to develop the closed loop block diagram. So, our process has the transfer function of k p 1 divided by tau p 1 is plus 1 and k p 2 divided by tau p 2 s plus 1 with opposite effects fine. The transfer function for the controller is G C. Input to the comparator is set point. Fine. Here we consider GM and GF both are equal to 1 for simplicity. So, this is the closed loop process. Fine. We have just included the transfer function for the controller with the process showing inverse response. Now, what is the open loop transfer function? Open loop transfer function we can write as y by y set point This is the open loop transfer function, and this can be expressed in terms of individual transfer function as Gc multiplied by Kp1 divided by tau p1 s plus 1 minus Kp2 divided by tau p2 s plus 1. Fine, because we assumed Gm Gf both are 1. So, Gc multiplied by Gp, this we can write as Gc Kp1 tau p2 minus Kp2 tau p1 s plus Kp1 minus Kp2 divided by tau p1 s plus 1 tau p2 s plus 1. Now, as we determined f prime for dead time compensator, similarly here also we need to find the expression for f prime. F prime is nothing but the output of the compensator. F prime is the output of the compensator, and this is written as Gc k 1 divided by tau p 2s plus 1 minus 1 divided by tau p 1s plus 1 y set point bar. Fine. Basically, this is the output y bar. No, this is not f prime, this is y prime. Y is the process output, y prime is the compensator output. Y prime is calculated so that ideally we obtain inverse free response, and that is y star. Y is the process output, y prime is the compensator output. If we add these two, we obtain y star, that is the ideal response, which is inverse free response. We did the same thing for the case of dead time compensator. And another thing I want to mention here, that this k, basically we will determine the condition based on this k. Fine, we will determine the condition based on the k. Anyway, now what is the ideal response? What should be the ideal response? Y star. Now we can calculate this y star, substituting the expressions for y and y prime. Substitute now. Gc multiplied by Kp1 divided by tau p1 s plus 1 minus Kp2 divided by tau p2 s plus 1 then k divided by tau p2 s plus 1 minus k divided by tau p1 s plus 1 multiplied by y set point. Substituting the expressions of y and y prime, we obtain this. This is y star. We can write this as Gc Kp1 tau p2 minus Kp2 tau p1 plus K multiplied by tau p1 minus tau p2 S plus Kp1 minus Kp2 divided by tau p1 s plus 1 tau p2 s plus 1 y set point. Rearranging the initial expression of previous expression, we get this. Fine. Can you find the expression for 0? What will be the expression for 0 which we can obtain from this expression? The expression for 0 will be minus Kp1 minus Kp2 divided by Kp1 tau p2 minus Kp2 tau p1 plus K tau p1 minus tau p2. Fine. Basically 0 we obtain by considering this numerator equal to 0. Fine. So, this is the expression for 0. Now, to avoid the inverse response behavior, this should be less than or equal to 0. Agree? The condition for inverse response behavior is this 0 should be greater than 0. Now, to avoid the inverse response behavior, it should be less than 0. Now, question is at what condition of k this is true? At what condition of k this is true? This is true when k is greater than or equal to Kp2 tau p1 minus Kp1 tau p2 divided by tau p1 minus tau p2. This 0 should be less than 0 when this condition is satisfied. Fine. Now, what is the transfer function for the inverse response compensator? The transfer function for the inverse response compensator we can write as k 1 divided by tau p 2s plus 1 minus 1 divided by tau p 1s plus 1. This is the transfer function for the inverse response compensator. Fine. This is the transfer function for the inverse response compensator. You just see the expression which we considered for y prime. This is the output. Output is inverse response compensator transfer function, then this is the controller transfer function multiplied by set point. So, it is obvious that this is the transfer function for the inverse response compensator, which I have written here. Fine. Now, we wish to incorporate the block of inverse response compensator in the closed loop block diagram, as we did for the case of dead time compensator. Now, our process has the transfer function of k p 1 divided by tau p 1 s plus 1 and k p 2 divided by tau p 2 s plus 1 they have the opposing effect, output is y. This is the controller GC. This is set point y. Now, we will place the compensator here. You see the transfer function of the compensator. The transfer function of the compensator can be expressed as k multiplied by 1 divided by tau p 2 s plus 1 minus 1 divided by tau p 1 s plus 1. Agree? This is the transfer function of the inverse response compensator. Definitely it is multiplied with GC. So, we can consider this input. Output is y prime and y is the output of the process. This is y. If these two signals are added, then we obtain ideal response, I mean inverse response, inverse free response. Fine. Now, if you see this expression, this expression y prime is the output, y prime is the output, that is multiplied, that is equal to GC, this is GC multiplied with k into this one, which is the inverse response compensator, then this is y set point, y set point. So, to obtain this y prime, this block is included in the closed loop block diagram. So, this is basically the inverse response compensator. Fine. Now, how, I mean at what situation we can get perfect compensation? At what situation we can get perfect compensation? If it is represented by k p 2 divided by tau p 2 s plus 1 minus k p 1 divided by tau p 1 s plus 1. This is the original transfer function of inverse response compensator. We can get perfect compensation if the inverse response compensator has this transfer function. Fine. You can substitute the y prime related to this expression in the expression of y star to see the perfect compensation. So, this is first point, we can get perfect compensation if the inverse response compensator has this form. Second point is inaccurate model degrades the inverse response compensator performance. Inaccurate model degrades the IRC performance. Inaccurate model degrades the inverse response compensator performance. So, this is all about the inverse response compensator. So, we discussed the two compensators, one is dead time compensator, another one is inverse response compensator. Fine. In the next we will discuss another advanced control scheme, that is cascade control scheme. Cascade control scheme. Previously we discussed three different controllers, P, PI and PID controllers, all are feedback controllers, and we will designate them as simple feedback control schemes. Previously we discussed P, PI and PID, which we are calling now simple feedback controller. Now, for those controllers, one measurement and one manipulated variable are involved. Fine. If I write a simple equation, I mean if I write a equation for the simple P only controller, we can write that as C equal to Cs plus Kc y set point minus y. This is the equation for P only controller. You see, in this equation the measurement y and manipulated variable C are involved, because Cs is the bias signal, which is basically constant, and Kc is the tuning parameter, and this is specified by the control engineer. So, in the simple feedback controller, one measurement and one manipulated variable are involved in a single loop. Fine. Now, we will discuss the cascade control scheme, in which more than one measurement and one manipulated variable are involved in cascade control scheme. For the simple feedback control scheme, one measurement and one manipulated variable are involved, but for the case of cascade controller, more than one measurement and one manipulated variable are involved. Secondly, it involves dual loop controller. The cascade controller involves dual loop controllers. One controller is called primary controller or master controller. Primary or master controller. Another controller is called secondary or slave controller. Fine. The cascade controller also involves a dual loop controller. First one is called the primary or master controller, and second one is called secondary or slave controller. Fine. Now, to discuss this cascade control scheme, we will take one example. We will consider the example of a jacketed CSTR. We will consider the example of a jacketed CSTR. This is a schematic of a jacketed CSTR. Inlet stream has the flow rate of F with concentration CAI and temperature Ti. Outlet stream has the flow rate of F, composition concentration Ca and temperature T. An exothermic reaction occurs in the reactor. An exothermic irreversible reaction occurs in the reactor. Now, the exothermic heat is removed by the coolant. Exothermic heat is removed by passing a coolant through the jacket. So, suppose the coolant flow rate is Fc and the temperature of the coolant is Tci. The outlet coolant flow rate is Fc and temperature is Tc. We assume that both the inlet and outlet flow rates are identical and they remain constant. Fi equal to F naught equal to F and they both are constant. For this example system, our control objective is to maintain the reactor temperature T at its set point value. The control objective is to maintain the reactor temperature T at its set point value. Now, we will try to find the pairs. Controlled variable is reactor temperature T, corresponding manipulated variable is coolant flow rate Fc, and possible disturbances are Ti and Tci. Fine. Control variable is reactor temperature T, corresponding manipulated variable is Fc and possible disturbances are Ti and Tci. Now, we will configure the simple feedback control scheme. We will configure the simple feedback control scheme. Inlet flow rate has the flow rate of F, concentration Ci, temperature Ti. Outlet flow rate is F, temperature T and concentration Ca. Fine. Our control objective is to maintain the temperature. So, first it is required to measure the temperature T by using a sensor, temperature measuring device. Then this measured temperature Tm is fed back to the temperature controller Tc. Measured temperature Tm is compared first with set point value Tsp, then the calculated control action is implemented through the final control element. Fine. This is the simple feedback control configuration. Temperature T is measured using the temperature measuring device represented by Tt. Then the measured temperature Tm is compared with set point value Tsp. Then the control action is calculated and that action is implemented through this valve. So, this is the simple feedback control configuration. Fine. Now, in this configuration, which one is the measured variable? Measured variable is T. Which one is the manipulated variable? Manipulated variable is Fc. Now, it is obvious that T responds much faster to changes in Ti than to changes in Tc. There are two disturbances, there are two possible disturbances, one is Ti, another one is Tc. Now, this T responds much faster to changes in Ti than to changes in Tc. T responds much faster to changes in Ti than to changes in Tc. It is very obvious, you see Ti can directly affect T because it is affecting to the reaction mixture directly, but Tc is first affect the jacket, then to the process. Fine. Tc is not directly going to the reactor, it is going to the jacket, then the effect goes to the, the reactor is affected then. Therefore, we can say that the reactor temperature responds much faster to changes in Ti than to changes in Tc. So, accordingly, can we say the simple feedback controller is more effective to reduce the effect of disturbance in Ti and less effective to reduce the effect of disturbance in Tc? The simple feedback controller is more effective to reduce the effect of disturbance in Ti and the controller is less effective to reduce the effect of disturbance in Tc. This conclusion we can draw based on this simple feedback control configuration. The simple feedback controller is more effective to reduce the effect of disturbance in Ti and less effective to reduce the effect of disturbance in Tc. Now, basically we want more effective for both the cases. The controller should be more effective to reduce the effect of Ti and more effective to reduce the effect of disturbance in Tc, and therefore, we need the cascade controller. Fine. Now, we will discuss the cascade control scheme, how it is more effective for both the cases. So, this is the CSTR, jacketed CSTR. Now, first we measure the temperature T using one temperature measuring device which we are representing by TT1. This is the first measuring device. I mentioned earlier that cascade controller involves more than one measurement. Fine. So, this is the first measuring device TT1. Then the measure temperature information, which is T suffix m. goes to the controller, temperature controller, which is TC1. Fine. Then the output of this first temperature controller goes to another temperature controller, that is TC2. The second measuring device TT2 is used to measure the disturbance Tc. This is negative, this is positive. and then the control action is implemented through this final control element. Fine. So, I am repeating the steps again. Our control objective is to maintain the temperature T. So, this reactor temperature is measured by the measuring device TT1. Then the measured temperature Tm is compared with its set point value. Then Tc1 calculates the control action. For the simple feedback controller, the control action of Tc1 is implemented, but here another controller is included, that is Tc2. Here the first temperature controller Tc1 calculates basically the set point value of coolant temperature. The first temperature controller basically calculates the set point of coolant temperature, that is Tc set point, and the second measuring device Tt2 basically measure Tc, which is a disturbance involved with the manipulated variable. So, this signal is basically Tcm, measured Tc. So, Tc set point is compared with Tcm, and the second controller Tc2 calculates the control action, and that action is implemented through this control valve. Fine. So, here Tc1 is the primary controller or master controller, and Tc2 is the secondary controller or slave controller. So, here two measurements are involved. One is reactor temperature T, and second one is coolant temperature Tc, but manipulated variable is one. I mean, only one manipulated variable is involved, that is Fc. Fine. For the feedback control scheme, there is no action with respect to any change in Tc, but this controller takes action if there is any change in Tc. This is the difference. So, disturbance in Ti will be taken care of by Tc1. And this is done by primary controller. Tc1 is the primary controller. This primary controller basically takes action after T is affected by Ti. This primary controller takes action after T is affected by Ti. I want to say that if there is any change in Ti, that should be reflected through T, then only the controller takes action. Fine. So, this disturbance first affect the process, then the controller takes action. So, disturbance in Ti will be taken care of by this primary controller, and it takes action after T is affected by T I. Next point is disturbance in T C can be efficiently compensated by TC2. This is the secondary controller. Fine. If there is any disturbance in Tc, that can be efficiently compensated by Tc2. This is the secondary controller, and it takes action before the effect of Tc is felt by the mixture. So, previously I mentioned that there are two possible disturbances, one is Ti, another one is Tc. Now, if there is any change in Ti, that will be taken care of by Tc1, and if there is any disturbance in another load variable Tc, that can be efficiently compensated by secondary controller Tc2. Fine, but primary controller takes action after T is affected by Ti, and secondary controller takes action before the effect of Tc is felt by the mixture. Fine. So, here two measurements are involved. One is T, another one is Tc, but manipulated variable is 1. I mean one manipulated variable is involved, that is Fc. Now, basically this jacketed CSTR consists of two processes. One is process 1. Process 1 is basically the reactor excluding the jacket. The jacketed CSTR consists of two processes. One is process 1, which is the reactor excluding the jacket, and here measurement variable is T, controller is Tc1. Another process is process 2, that is the jacket, and for process 2 the measurement is coolant temperature and controller is Tc2. Fine. So, the jacketed CSTR consists of two processes, one is process 1, another one is process 2. Process 1 is the reactor excluding the jacket, and process 2 is the jacket. Fine. So, in the next class we will derive basically the closed loop block diagram for this cascade control scheme. Thank you.